Imagine snapping a single photo of a busy scene and asking a model to rebuild every object in full 3D. Not just the visible surfaces, but the hidden sides too. That is the goal of SAM 3D. The idea is simple to say, but hard to do. SAM 3D takes one image and predicts shape, texture, and the position of objects in space. It works even when scenes are messy or objects are half hidden. The trick is in the training recipe. The team starts with synthetic objects, then mixes in semi-synthetic render and paste scenes, and finally adds real images where humans pick the best 3D candidates from model-generated options. By repeating this loop, SAM 3D keeps getting better at turning a single picture into a complete 3D world.
All right, let's dive into this paper. The first thing you'll probably notice is the clever title, which is a direct nod to the famous Segment Anything model, or SAM. We'll be using the abbreviation SAM from now on. The title sets a high bar, suggesting this model aims to do for 3D reconstruction what SAM did for 2D segmentation. Make it general and work on pretty much anything. The abstract quickly lays out the core challenge. Getting 3D models from a single, messy, real-world photo is incredibly hard. I mean, think about it. Objects are often partially hidden, and the lighting can be all over the place. The authors state their model, SAM 3D, is designed to excel at this very task. So how do they pull it off? They highlight two key innovations. First, they tackled the biggest bottleneck in 3D research, the lack of data. They created a new pipeline that uses both humans and AI to generate a massive dataset of 3D objects from images. This is a huge deal, because good data is often the most important ingredient. Second, they use a modern, multi-stage training strategy. They pre-train their model on clean, synthetic 3D data, and then fine-tune it on their new, messy, real-world dataset. This two-step process helps the model learn the fundamentals of 3Ds before it has to deal with the chaos of reality. Now take a look at Figure 1. It really brings this to life. You can see the model taking a regular photo of a room and then basically pulling out individual, fully 3D objects from it. A chair, a plant, a lamp. It does the same thing with a street scene, where it extracts a complete 3D bicycle and car. This isn't just creating a flat, 3D-looking image, it's generating actual 3D assets you could use in a game or a simulation. The introduction reinforces this point, explaining that the goal is to create a full 3D shape, not just a 2.5D surface, which is basically a depth map of what's visible. This model is trying to guess what the back of that chair looks like, even though it can't see it. That brings us to the heart of the biggest problem in 3D computer vision: the massive data shortage. The authors point out that while previous models have shown promise, they're usually trained on clean, isolated objects. That just doesn't prepare them for messy, real-world photos where things are partially hidden or far away. So they present their big idea for solving this. It's based on a simple but really effective insight. Humans are not great at creating 3D models from scratch, but we're excellent at picking the best option from a list. So instead of asking annotators to do something incredibly difficult, they have a model generate several possible 3D shapes for an object in a photo. The human's only job is to pick the best fit. This is a game changer for scaling up data collection. They call this a model-in-the-loop pipeline, and it creates what they call a virtuous cycle. The model helps the human annotators, and the high-quality data from the humans is then used to retrain and improve the model. As the model gets smarter, its suggestions get better, and the whole process gets faster and more efficient over time. To make the model robust, they use a 3-stage training recipe, which is very similar to what's done with large language models. First, they train it on purely synthetic 3D data to learn the basics. Next, they use semi-synthetic data, that's 3D models pasted onto real backgrounds. And finally, they fine-tune it using the data from their new human-in-the-loop pipeline to align the model with real-world complexity. It's a smart, layered approach to a very difficult problem. Okay, now we get into the nitty-gritty of the model's architecture, and it's laid out beautifully for us in Figure 2. The whole system is like a 2-act play. Act 1 is the geometry model, and its job is to figure out the rough 3D shape and where it sits in the world. Act 2 is the texture and refinement model, which takes that rough draft and turns it into a high-fidelity, textured 3D object. Let's start with Act 1. The model is smart about its inputs. It doesn't just look at a cropped-out picture of the object, it also looks at the entire image. This gives it crucial context. A chair in a living room looks different from a chair on a store website, right? The model needs to understand that. The core of this stage is a mixture of transformers that works on two things at once: the object's shape and its layout. which means its position, rotation, and scale. Now here's the clever part. The layout part of the model can look at the shape part to make better decisions, but the shape part is forced to figure out the object's geometry on its own, without cheating by looking at the layout. This makes sense. A chair is a chair no matter where you put it. The output of this first stage is a coarse, 3D shape, kind of like a blocky model made of voxels, along with its exact coordinates in the scene. Now for Act 2, the refinement stage. This part takes that blocky voxel shape and the original image and goes to work. It uses another transformer to add all the fine details and paint on the texture. What's really interesting is the output. It can generate a standard 3D mesh, but it can also create a 3D Gaussian splat. This is a very new and powerful way to represent 3D objects that's great for photorealistic rendering. It's a very modern and flexible design. This section is all about the data, and Figure 3 is a fantastic visual breakdown of their training strategy. It shows the 4 different flavors of data they use, and it's like a curriculum for their model, starting with easy lessons and moving to the really hard stuff. First up, you have isolated 3D objects. This is the kindergarten level. Think of perfect, clean, 3D models of things like a duck or a shirt on a plain white background. This teaches the model the absolute basics of what different objects are supposed to look like in 3Ds, with no distractions. Next, they graduate to render-paste 3D objects. This is like middle school. They take those clean 3D models and digitally paste them into real photos. So you might see a 3D stool sitting in the middle of a real-life market. This forces the model to learn how to find and understand an object's shape, even when it's surrounded by a busy, realistic background. Then comes the high school level, MITL 3D objects. This is their secret sauce. These are real objects in real messy photos. The 3D models for these were created using their clever human and AI in-the-loop system. This is the data that really teaches the model to handle the chaos of the real world, weird angles, partial visibility, and complex lightings. Finally, you have the final exam, Artist 3D objects. This is their benchmark dataset. They took really challenging objects in photos and paid professional 3D artists to create perfect 3D models of them. This data isn't for training, it's for testing. It's the gold standard they use to measure how good their model really is. It's a really comprehensive and smart way to build and evaluate a model. Alright, so we have the architecture and the data. How do they put it all together? This page gives us the master plan for how SAM 3D is trained, and Figure 4 lays it out perfectly. It's a multi-stage journey, and they've borrowed some of the best ideas from how large language models are trained. It all starts with synthetic pre-training. They take a huge library of clean, synthetic 3D models and use a render engine to create tons of 2D pictures from them. This is the model's bootcamp. It learns the absolute basics of 3D geometry here, like what a chair looks like from the top, side, and front. Next is semi-synthetic mid-training. Here, they take those same 3D models and digitally paste them into real-world photos. This teaches the model to find and understand objects even when they're surrounded by visual noise and clutter. It's a crucial step to bridge the gap between the clean synthetic world and messy reality. Then comes the main event, real-world post-trainings. This is where they use the data from their special model-in-the-loop, or MITL, pipeline. We'll use MITL for short from now on. The model is fine-tuned on real images, with 3D annotations created by that human AI team. This is what gives the model its ability to handle the wild. But they don't stop there. The final step is preference optimization. They use a technique called direct preference optimization, or DPO, which is very popular in the LLM world. They show humans different 3D outputs from the model and ask, which one looks better? This feedback is used to tweak the model so its results aren't just accurate, but also look good to a human eye. The whole process is an escalating curriculum that takes the model from a simple student to a sophisticated expert. Let's zoom in on those first 2 steps of the training process, pre-training and mid-training. This is all about building a solid foundation for the model before it ever sees the messy, real-world data. If you look at Table 1, it gives us a super clear, step-by-step breakdown of this. First, the pre-training phase. The goal here is simple. Teach the model what 3D objects look like in a vacuum. They use a massive dataset of 2.7 million clean, isolated 3D models. The model is shown a picture of an object, like a chair, and its only job is to reconstruct the 3D shape and texture. It's like learning vocabulary from flashcards. The geometry model learns the basic shapes, and the texture model learns the basic appearances. Next comes mid-training, which is where things get more interesting. The model now has to learn how to handle objects in the context of a real scene. They do this with their render-paste dataset, where they digitally place 3D objects into real photos. This teaches the model 3 crucial skills. First is mask following, just paying attention to the object you care about. Second is occlusion robustness, learning to guess the full shape of an object, even if part of it is hidden. And third is layout estimation, figuring out exactly where the object is in 3D space. By the end of this mid-training phase, the model has a strong set of foundational skills. It knows basic shapes and textures, and it knows how to find them in a busy image. But, as the authors point out, all the data so far has been synthetic or semi-synthetic. And to truly master the task, it now needs to learn from the real world. And that brings us to the final and most critical part of the training: real-world alignment. This is where the model, having learned from clean synthetic data, finally gets its hands dirty with messy, real-world images. The goal is to close that gap between the classroom and reality. The whole process is powered by their data collection pipeline, which is laid out perfectly in Figure 5. Let's follow the journey of a single object, like a couch in a photo. First, in Stage 1, a human annotator simply points at the couch, and with the help of the Segment Anything model, a perfect 2D outline is created. Simple enough. Stage 2 is where the magic happens. The system shows the human annotator a few different 3D couch models that the AI generated. The human's job isn't to build a 3D couch that's incredibly hard. Their job is just to pick the best one from the lineup, like a judge on a game show. This simple idea is the key to creating data at a massive scale. Of course, when the model is just starting out, its suggestions might not be great. The authors call this the cold start problem. To get going, they use a whole team of different models to make suggestions. But as their main model gets better from training on this new data, it starts making better and better suggestions itself, creating that powerful self-improving loop we talked about. Finally, in Stage 3, once a good 3D model is chosen, the human just has to nudge it into place, adjusting its position, rotation, and size until it fits the couch in the photo perfectly. By breaking the problem down this way, they were able to create a dataset with millions of 3D annotations, something that was pretty much unthinkable before. So after all that work on data and training, does it actually pay off? This is where we see the results, and Figure 6 is the main event. It's a head-to-head comparison of SAM 3D against a whole lineup of other top models, and the difference is pretty clear. You can see it row by row. They take a challenging object, like a folding chair with all its thin legs, and show what each model produces. The other models spit out these wavy, distorted messes that barely look like a chair. But SAM 3D's result is clean, sharp, and structurally correct. It looks just like the ground truth model made by a professional artist. It's the same story for every example. For the elephant, SAM 3D produces a recognizable animal, while the others create lumpy blobs. For the incredibly cluttered table of food, where other models completely fall apart, SAM 3D manages to understand the basic structure of a flat table. This visual evidence shows that their entire pipeline, the careful pre-training, the semi-synthetic mid-training, and especially the massive real-world data from their human-in-the-loop system, really makes a difference. The text then explains how they use all this new data to actually improve the model. It's an iterative process. They start by fine-tuning the base model on the high-quality data they've collected. This helps bridge that huge gap between the clean synthetic world and the messy real world. As the model gets better, they can even raise the quality bar for the data they collect, creating that virtuous cycle we talked about earlier. It's a continuous loop of collecting data, training the model, and then using the better model to collect even better data. The model isn't just good with single objects. It can handle entire scenes. Take a look at Figure 7, which levels up the comparison. And again, SAM 3D's results stand out. In the first row, you see a super cluttered table. The other models produce a chaotic jumble of 3D shapes. But SAM 3D correctly identifies and separates the different items: the bowl, the bottle, the little wooden pallet. It understands the scene's layout. The same is true for the dining room scene. SAM 3D builds a proper table with 4 chairs, while the others create a distorted mess. This shows the model isn't just good at recognizing things, it's good at understanding how they fit together in 3D space. The text also explains the final steps of their training process. After the main fine-tuning, they do preference optimization. This is where they use human feedback to teach the model about subtle qualities that are hard to write a loss function for, like symmetry, or making sure an object has a solid base instead of floating. They use that DPO technique we mentioned earlier, which directly learns from "I like this one more than that one" style feedbacks. Finally, they use a process called distillation to make the model faster. This is like a skilled master teaching an apprentice. They train a smaller, faster model to mimic the big, powerful one, so it can generate results in a fraction of the time without a huge drop in quality. With the model fully trained and optimized, they're ready to move on to the formal experiments. Alright, after all the impressive pictures, this page brings the receipts with cold, hard numbers, and the story they tell is just as compelling. First, let's look at Table 2. It's a scoreboard with a bunch of different metrics that measure how accurate the 3D shapes are. The most important part is the comparison on their new, super tough SA3DAO benchmark. Here, SAM3D doesn't just win, it completely dominates. The scores for accuracy are way higher, and the scores for error are literally half of the next best model. It's a massive leap in performance, especially on the messy, real-world images that other models struggle with. But numbers can be abstract. What really drives the point home is Figure 8. This chart shows the results of human preference tests. They basically put the 3D models in a lineup and asked real people, which one looks best? The results are pretty striking. The giant dark blue bars show that for both single objects and full scenes, people chose SAM3D's output about 80% of the time. The text puts it perfectly. It's a 5-to-1 win rate for objects and an even more impressive 6-to-1 win rate for scenes. This is the ultimate validation. It means the model isn't just better according to some mathematical formula. It's producing results that are visibly and dramatically better to the human eye. This is what all that hard work on the data pipeline and training strategy was for. The model's superiority isn't just in the overall shape, it excels in specific areas like layout and texture. Let's break that down. First, check out Table 3. This looks at layout, how well the model places objects in the 3D scene. It compares SAM3D's joint approach, which figures out shape and position all at once, against pipeline methods that do it in separate steps. The numbers are decisive. SAM3D is significantly better than the pipeline methods on every metric. This is a big deal, because it shows that understanding shape and context together leads to a much more accurate result. It's a strong argument for an end-to-end approach. Next, Figure 9 tackles texture quality. To make the comparison fair, they did something really smart. They gave every model the exact same high-quality 3D shape, generated by SAM3D of course, and said, okay, now just paint the texture on it. This isolates each model's texturing ability. And once again, it's a landslide. The bar charts show that humans overwhelmingly prefer the textures generated by SAM3D, especially on the challenging real-world data. Finally, the paper briefly touches on some analysis, confirming that their core ideas work. They show that running their data collection and training loop for longer steadily improves the model, and that every single stage of their multi-stage training process, from synthetic pre-training to real-world fine-tuning, is crucial for achieving the final performance. This final section of analysis really ties a bow on the whole paper by proving that their core ideas work exactly as they claimed. It's all about validation through careful experiments. First, Table 4 is a classic ablation study. It's like deconstructing a recipe to see if every ingredient matters. They start with just the base pre-trained model, and then, row by row, they add each training stage back in. The results are crystal clear, with every single step. From mid-training to fine-tuning to preference optimization, all the performance metrics get better. This proves their multi-stage training strategy isn't just a bunch of random steps. It's a carefully designed curriculum, where each lesson builds on the last. Then, Figure 10 provides the smoking gun for their virtuous cycle data engine. They use an ELO rating system, just like in chess, to rank their models over time. Chart A shows a beautiful, steady climb in the model's skill level with each new version. This is the flywheel in action. A better model helps collect better data, which creates an even better model. Chart B confirms this, showing that each new batch of data from their alignment process gives the model a significant boost. The paper then wraps up with a related work section, placing their contributions in the context of decades of 3D research. They acknowledge the foundational work, but clearly state how their approach, particularly in tackling the data problem for in-the-wild scenes, is a major step forward. To wrap things up, the authors place their work in the broader context of machine learning and then give a final, concise summary. They finish the related work section by connecting their training methods to the latest trends in large language models. They point out that ideas like multi-stage pre-training and using human feedback for alignment aren't new, but they are the first to successfully adapt this powerful playbook to the challenging domain of 3D vision. It's a smart way to show they're building on established ideas while also carving out their own unique contribution. Then comes the conclusion, which is short and sweet. They state their case clearly. They've created SAM 3D, a new foundation model for 3D reconstruction. They emphasize that its success comes from two key things: the innovative data engine that finally broke the 3D data barrier, and the modern, multi-stage training recipe. They end on a forward-looking note, suggesting that this work could unlock new capabilities in all sorts of exciting fields, from robotics and AR/VR to gaming and film. It's a powerful closing statement that frames their work not just as an academic achievement, but as a foundational technology for the future. Thanks for joining us today. Happy exploring together.